Hi everyone, welcome to not the deep learning talks but the weekend white paper. So this weekend or this whole week was all about exploring the time and the tenure when we were introduced or when we were being introduced to GPT-3. So we had seen GPT-2 and how we are transitioning from GPT-2 to GPT-3. So in this particular era, we had something known as BERT, and we had something known as the idea of fine tuning. So for every custom domain specific use case, we used to fine tune models, right? And the only learning that we believed in was gradient based learning, parameter update learning, right? So we know that in any in any model, no matter whether we are using a simple neural network or a classical machine learning algorithm or any sophisticated large language model, learning is the stage that we consider where the weights of the network or the model gets updated, right? So weights and parameter based learning obviously is expensive. It is time expensive, compute expensive, data expensive, right? So we observed something in this particular paper, that there is a concept which is known as in context learning. Sorry, excuse me. In context learning, where you provide a lot of context or few examples in the prompt itself, and then you observe the behavior of these large language models. So in context learning and the idea in the experimentation, all of the experiments that were done at the OpenAI lab are documented in this paper, which is known as language models are few short learners, right? So this paper gives us an understanding of no new architecture, but a new paradigm to look at things, right? How do you view in context learning as the idea of learning? The paradigm to view large language models also kind of shifted after this paper. GPT-3 brought in no new architecture, but uh, multiple hypotheses were proved during this paper. The scaling laws, the power laws, the compute laws. I mean, and proving how more and more examples in the prompt gets you better and better results. All of these things happened during this particular time, right? So the paper is titled as "Language Models Are Few Short Learners." This paper has come from OpenAI, and yeah, we're going to go through this paper. So it's a 75-page long paper. I have opened it on my monitor, and we're not going to go line by line on this paper, but we're going to capture all the important plots and hypotheses that has been kind of experimented with, and we are also going to understand a few paradigm shift that happened. So knowing the past always helps. So when this paper came, knowing the past always helps because we'll be able to gather more context on why they are kind of solving this problem. Who is asking them to solve this problem? So first thing is obviously they're advertising GPT-3. Second thing is they came up with a very large model. From the current state of the art, they came up. So for example, if you want to imagine the scale, if I remember correctly, at this particular time when this paper was introduced, the largest model that we had close to 13 to 15 billion parameters. Now this paper introduced 175 billion parameters, right? Or not this paper, but the architecture or the architecture and the launch of GPT-3. So all the experiments that have been captured in this paper are to also market GPT-3, to advertise its capabilities, and to give you a few paradigms to view GPT-3 and to view the idea of language modeling, right? So you will learn a lot of new concepts in this particular video, and a lot of new paradigm shifts that happen. You will not learn a new architecture, right? So if we are aiming that we this paper is going to be very architecture heavy, this is an applied AI paper. This is a lot of experimental AI paper, right? This is not a theoretical, proof of a certain architecture or a proposal of a new architecture. No. So they did a lot of research. They built up a new model, which is GPT-3. The architecture remained the same. It is also a decoder only dense transformer, and they kind of wanted to push, uh, you know, the idea of in context learning, zero shot learning, few shot learning, one shot learning. So there are three paradigms. to view in context learning uh, with zero examples, with one example, and with few examples. They proposed which one is better and which one is superior, right? And along with that, scaling loss, and how loss is inversely proportional to the capacity to the scale, right? So as you increase the scale of what? Scale of training data, scale of compute, scale of model complexity, right, which is the number of parameters. You will see that the cross entropy loss, the log loss, will have a decline, right? So if we keep on increasing the scale, the loss is very much inversely proportional. It gives you a decline, right? It's not and it has a linear relationship that it follows. So all of these things are kind of experimented in this paper, and they have been put up as graphs. So we will observe the graphs, because graphs give us a lot of detail, right? We don't want to get into the detail of when this experiment was performed, which was the precise machine. We want to understand how, what we can infer from this, what we can take as a wisdom from this paper, right? So we'll go into the details of the graphs, and then we will look at what all new concepts should be internalized, what are the takeaways, right? So a lot of learnings from graphs and a lot of takeaways from the paper. This is going to be a blend of information that we're going to absorb from this paper. Okay, now let's get started. A lot of jibber jabber. Now let's look at the first graph that is a little meaningful to look at. Now, this particular graph, I would not call it a graph, but let's call it a figure. Okay, so the figure is titled as language model meta learning. Okay, we don't know what is meta learning yet. We don't know what is in context learning, but let's try to observe. So what we are showing in the outer loop on the horizontal axis, learning via stochastic gradient descent during unsupervised pre-training. Okay, so this is a traditional learning, right? So they're saying that this is the axis which is representing the parameter based learning, the weight update based learning, the gradient based learning. All of these things are, they mean the same. Now what do we have here? The first example is an addition of two numbers. 5 plus 8 is equal to 13, 7 plus 2 is equal to 9. So imagine that all of this is nothing but a prompt, right? Now here all of this is nothing but a prompt, right? And this also is a prompt. So what are we trying to do here? We are trying to correct a few spelling mistakes, or map them to the correct spelling. Here we are trying to perform addition on two numbers. Yeah, all of them are additions. And here we are trying to perform translation. Thanks is merci, so this is French. Hello is bonjour. Mint is menthe. Wall, mer. Then bread, pain. Okay. So we have this in context learning examples across different tasks. The first task we have catered to is the addition operator, which is like a simple algebra. Then the second task is correcting the mistakes in the spellings, right? And third task is translating each particular word from English to the other word in French, right? So what we are trying to prove here is that you have gone through a lot of training during your pre-training phase, and a lot of training that you went through was unsupervised, where you tried to make sense of the whole language or the internet that was presented to you. That is your stochastic gradient descent or gradient based learning or your training. Now here, if you give a few context in the prompt, let's say I give 1 2 3 4 5 6, let's say 6 examples of addition, and then I ask the model to do the seventh addition itself, it is going to do that seventh addition, right? Same here, right? Can it also do the seventh addition without this? Obviously yes, it can do, right? But the idea that I am instructing it to follow a particular representation of addition is given in the prompt. This is basically known as in context learning, that the model internally builds a representation of your provided data. This data is not part of your training. This data is part of your prompt. So training happens during training phase. prompting happens during inference phase. The model weights are already stored somewhere. You are just trying to call the dot predict function. In the dot predict function, you are mentioning all of these addition examples as part of your prompt, right? So let's try to read through the description of this. So during unsupervised pre-training, a language model develops a broad set of skills and pattern recognition abilities. Definitely. So a language model's whole purpose is to to produce a representation of the whole language that it is trained on, or the whole training data, and then store them as weights. I mean, remember or memorize those representation, learn those representation in the higher dimension. We also call them token embeddings, and we also call them various sets of embeddings. We have token embeddings, positional embeddings, attention embeddings. All of these things are learned, right? And they are in higher dimensions. That is the whole idea of language model. And then you use those representation and those learned abilities at inference time to rapidly adapt or recognize the desired task, right? So instead I say, can you add two numbers 10 plus 2? So it's going to give me a very verbose answer. Let's say, okay, let me think about it. 10 plus 2 is 12, and it is 12 because it follows this particular linear algebra. Oh, sorry, it follows this particular mathematics algebra operation, blah blah blah. Now if I give it certain examples and then I ask it to do 10 plus 2, it's strictly going to follow this particular format, right? This is the idea of in context learning. We are triggering the model and instructing the model that this is the format that you should follow. This is how addition is done. Here are few examples, and you have to reciprocate this, right? So we use this term, which is known as in context learning, to describe the inner loop of this process. So this is basically the inner loop, and this is the idea of in context learning, which occurs within the forward pass upon each sequence. So what does this mean? So why does it say that it occurs during the forward pass? The in context learning only occurs during the forward pass. What if it were to occur at the backward pass? If it were to occur at the backward pass, we would simply call it training, right? So every neural network, every transformer, every classical machine learning model, okay, I cannot say every classical machine learning model, but every neural network and every transformer has something known as forward pass, where it goes from left to right? Then it computes loss here after the forward pass is done. Then it back propagates, right? In the forward pass, it is computing y is equal to mx plus c. After the forward pass, it is computing the loss, where it is computing yi hat minus yi whole square divided by n, which is, let's say, your root mean squared loss, or maybe cross-entropy loss, right? Then at the backward pass, it is differentiating the loss with respect to all the parameters in the forward pass. Let's say the forward pass has hundreds of parameters nested MNC, because there are hierarchical layers, right? So all of them are going to be updated in the backward pass, right? So forward pass, compute loss, backward pass, forward pass, compute loss, backward pass. Now when we call the predict function of the transformer, which is the inference stage, in the inference stage, it is only the forward pass that happens, right? So because let's say if forward pass is named as y equals to mx plus c, okay, if I want to predict, given x, I want to predict y, m and c are already stored, right? They're computed because the training has been done. Once the training is done, I freeze the weights. And I use the weights to compute my y every time, right? When I'm computing my y every time, given the frozen weights and given the input x, this is what is known as dot predict phase, or dot inference phase, or dot forward pass, right? So this is the idea of forward pass. So no typical back propagation, gradient descent, parameter based update learning happens here, right? We're simply computing y given all the weights and given the input. That's it, right? So we are simply instructing that in context learning only happens during the forward pass, right? Formally, see, it's not really learning that is happening in the forward pass, but as an abstract idea, we call it in context learning, right? Because the model already has learned these examples in their training data. Now, in context learning is something that triggers the model, and it triggers the model to get that information from its latent representation space and follow that, right? It already has seen a lot of French, right, in the training data. Now when I give it certain examples, now in this forward pass, the model is going to go and look at its representation that it has learned during the training phase, and it's going to trigger those particular weights where all the French modeling it saw, and then it's going to respond as a French English to French translator, right? So that's why we call it learning, because something gets triggered in the forward pass, but since we are not updating anything, we are not updating the gradient, I mean we are not updating the gradient vector, we are not computing gradients, we are not updating the weights and parameters, it's not formally learning as per se, right? So yeah, this is the idea of in context learning, this is the idea of examples. And now let's get into the second figure, which is also very crucial and very important. Okay, so as I was saying, that this paper is also an advertisement of GPT-3, right? When we say advertisement, we don't simply mean that they are trying to promote GPT-3. We are simply trying to say that they are signaling the architecture of GPT-3 and its performance based on the other state of the art models at that particular time. So GPT-3 was a fairly large model. We all know that, right? We can see that uh, the jump went from 1.3 billion parameters to 13 billion parameters, and then to 175 billion parameters, right? Now, on the horizontal axis, I have kept something known as number of examples in the context, right? So here we had how many? I think 2, 1, 2, 4, 1, 2, 6, 6 examples, right? Here we are, noting down the number of examples that we perform in the experiment. On the vertical axis, we have something known as accuracy. Now, accuracy obviously goes from 0 to 100, and here the number of examples are also going from 0 to 100, because 0, 1, then 10, then 100, right? So 100 here, 100 here, 100 examples, and then obviously you're benchmarking against accuracy. Now, what is this graph? Now, let's talk about this graph. What can we infer from this graph? Let's try to observe it closely, right? First thing is we want to make sense of what we are trying to do. We are trying to plot performance of each model. Green is a model, orange is a model, blue is a model, right? And we are trying to plot the performance against only one specific task. I think the specific task that has been you know that the task that has been computed here is nothing but removing random symbols from a word, right? So this is the task. So every benchmark, or every benchmark has a particular use case, right? So we will look at a couple of benchmarks. Some benchmarks test the model on its long reasoning capability, some benchmark test the model on its Q&A ability, some benchmarks test the model on its mathematical and logical reasoning ability, right? So this particular this particular experiment mentioned in this particular plot, this is not a benchmark, but this is a specific task. The specific task here that we tried to perform using the model is removing random symbols from a word. All of these three models, whether small or big, are performing the same particular task, and we are observing the accuracy, right? The first, I mean, we start at this point where all the models perform with zero examples. Zero shot means in the prompt you did not mention any particular example, right? So you did not tell which word to remove, you did not demonstrate the model in the prompt what to do. So that is zero shot, right? So okay, all of the results are more or less the same, right? No matter if you're a big model or a small model, all of you are performing little poorly, or little poor, I would say. Then one shot is what? One shot is when you give one example, right? Now if I give one example, there is such a steep increase in the 175 billion parameter model. Then there is also some increase in the 13 billion parameter model, and there is very little increase in the smallest model, right? What can we infer from this? We can infer that giving one example is definitely beneficial for all types of language model, because no language model had a decline in performance. All of them had a linear or non-linear increase in performance, right? The second thing that we can infer is, bigger the model, bigger the impact, right? This is the biggest model. The biggest model had the biggest impact even with one single example, right? So that also means that uh, bigger models tend to do better with context. Smaller models might only increase their performance linearly, but bigger models tend to do a lot better if you give some context, right? So this is the whole idea of this particular plot, right? So we can see and prove with experiments that 175 billion parameter model did the best in one example, and then 10 examples, and then obviously at 100 examples, right? But whereas the smallest model, it did well, okay, but the increase in performance is super linear, right? It could have done such so much better. So we can also say that obviously in context learning is cool, but in context learning on large models, large parameter models is super cool, right? The effect on the performance is magnified, right? Okay, now let's go to the other plot that is worth observing, and it's a little complex plot, but let's have a look at it. Now, what do we see here? On the horizontal axis, we see the model complexity, the number of parameters in the model. As we go on the extreme right, the size of the model increases, the complexity of the model increases, the number of parameters increases. On the vertical axis, we see something known as accuracy, right? And okay, so we call this plot as aggregate performance for all 42 accuracy denominated benchmarks. Okay, so we are trying to use a benchmark here. That benchmark is testing these three strategies, right? With a few examples, with one example, and with zero examples, right? And it is testing models of different sizes, right? So we are also trying to demonstrate here the efficiency or the significance of in context learning, right? So what can we see here? Few short performance increases more rapidly, right? If we have a large model and if we are using few shot strategy, it is far better than a smaller model. Let's say if we compare this particular data point to this particular data point, right? And assuming that this is logarithmic scale, right? So when we say logarithmic scale, so the difference is not this much, it's very inflated, right? So what we can also infer, no matter what, a few examples is a superior strategy. Hands down, it is a superior strategy, right? And one example is also a nice strategy if we compare it in relation with zero examples, right? And in context learning genuinely happens, right? So when we say in context learning genuinely happens, is we simply mean that the model genuinely tends to perform better only with a certain examples in the prompt, without going through the back propagation, the weight updates, the parameter updates, the computing of gradients, and the typical training cycle, right? And bigger the model, more is the effect, right? So here bigger models tend to do even better on the same benchmark, right? With a few examples. That means having bigger models is a superior strategy. On top of that, having few short examples in the prompt when capped up with the bigger model is a far superior strategy, right? As compared to no examples and smaller models, right? Okay, now let's look at one more. I think it's figure 3.1 that I would like to look at. Yes, now this is also a very good example, or a very good figure, right? So let's look at this plot. Now on the horizontal axis, we are computing something known as compute, right? So the size of the compute, as we go on the right, we keep on increasing it. It's denoted by petaflops per second days. On the vertical axis, on one side we have the model complexity, the number of parameters, and on one side we have validation loss. Okay, so what can I infer from this model? Oh, sorry, what can I infer from this plot? So I can infer that. So this is nothing but your cross entropy loss. This is nothing but your log loss. I can infer that there is a linear relationship between the cross entropy loss and the compute, right? What I mean by that is, and this linear relationship is inversely proportional. As I keep on increasing the compute and I give more and more compute to my model, it has the ability to bring down the loss, which is the cross entropy loss. Lesser the loss, more the compute, better the model, right? So let's put, I mean, read through this particular title. So the title of this plot is smooth scaling of performance with compute, right? So I mean, what we are saying is compute is a good enough scaling parameter to increase the performance of the model, and to bring down performance is also correlated with accuracy and loss. So if the validation loss is coming down, that means we are increasing the performance. Performance is measured in terms of cross entropy validation loss. In this particular plot, it follows a power law. It Power law trend with the amount of compute used for training. The power law behavior observed in KMH plus 20 continues for an additional two orders of magnitude with only small deviations from the predictive curve, right? So we are I mean, we can clearly see that this is also a relationship that has been mentioned. L is equal to 2.57 into c to the power negative 0.048. So this basically means nothing, but it simply says that as you increase the model size, as you increase the training data, the compute, which is GPU and time, your training time, the loss decreases in a very predictable, deterministic, mathematical way, right? It's not random, it is not chaos. I mean, we can take a bet on adding more compute to the model, because we know that is going to increase the performance, right? So this is what this model is, this plot is trying to prove. Okay, now let us also go to the next one. Yeah, I think we can look at uh, this particular plot also. Okay. Okay, so this plot is also a series of experiment that is worth observing. Let's look at figure 3.2. Okay, now on the horizontal axis we again have parameters that are in billions, and on the vertical axis we have accuracy to measure the performance. And the benchmark that we are treating here is, so we are targeting multiple benchmarks, but for this particular plot we are targeting lambda, right? So this particular benchmark has the capability, to focus on long range context for word prediction, right? So I mean, we'll go through two benchmarks here. One is trivia QA, which is focused on question answering, and the other is lambda. So it focuses on understanding long range context for word prediction, right? So if we try to understand this particular plot, we'll be able to again infer the same insights that we observed. So what were those insights? So the insight was, as you go and keep on increasing the model complexity and the model size, your performance increases. Now, as you go on increase the model complexity and model size with a few examples, which is known as in context learning or few shot learning. Here we have taken 15 examples, k is equal to 15. On lambda benchmark, you tend to do genuinely better, right? And I'm guessing this plot is also on log scale, so each small increment is 100x increment, right, in performance. So on the zero shot examples, we don't really do that well when it comes to few shot examples in case of lambda, right? But we can see that one shot does not have a great effect on larger models. One shot is not as good as few shot, right? But few shot is definitely far superseding, right, on lambda benchmark. So what that also mean is that we are able to prove that it's not only very simple calculations or simple translation or simple tasks that are good for few shot learning. Even when we want to test a data uh, or a benchmark that tests your model on long range contexts, few shot is still better there, and larger models are still better there. right? So we are kind of proving both the hypothesis that larger models are better. They provide better intelligence on long range context tasks and on small, simple, effective tasks, and few short examples. Providing few short examples is always a superior strategy, and especially when you provide few short examples to bigger models, they tend to do far better, right? So it's like, you know, the expansion is seen on both the ends. So all of these are benchmarks that have been mentioned here: Hella Swag, Story Clause. Let's look at one more plot. This is also worth noting, which is the Trivia QA. This is also a benchmark. Let's go read something about it. So Lambda and Trivia QA are both prominent yet distinctively different benchmarks used to evaluate LLMs and NLP tasks. Okay, now Lambda focuses on uh, design for language modeling. It focuses on understanding the broad preceding context, right? It focuses on understanding long range contexts for word prediction. Whereas Trivia QA is a large scale reading comprehension dataset focusing on question answering based on evidence documents, right? So it's like how we test trivia knowledge or general knowledge for humans, right? So it's like a simple open book and closed book test, and both of them have different data set structure and evaluation structure, right? So both of them are good enough benchmarks and very standard for the industry. Now on Trivia QA, GPT-3 performances grow smoothly with model size. We can see that, right? So GPT-3 is the 175 billion parameter model, and we can see that as we provide a few examples, the performance is increasing. As we increase the size, the performance is increasing. So this particular experiment also proves our previous proceedings that this is a superior strategy. Few short is a superior strategy. Having larger models is a superior strategy. We have proved it on almost all the possible standardized benchmarks. Okay, now let's go to another figure. Yeah, I think let's look at this also. This is also worth noting. Oh, so what are we trying to do here? We here also we have some parameters on the horizontal axis, where we go from a 0 billion parameter model, or sorry, a few millions parameter of model, then to 175 billion parameter model. Then obviously on the vertical axis we again have accuracy. Here we are performing multiple tasks: two-digit addition, two-digit subtraction, three-digit addition, and with few short examples. So we can see that few short is performing the best in two-digit addition, right? And let's also see the worst. Five-digit subtraction, it is performing the worst, right? So I think more and more digits, as we go with more and more digits, because here two-digit addition subtraction are peaking with few short examples. That means the examples are working really well when we only have two digits, whether we are adding or subtracting. Obviously addition is far superior. Then three-digit addition is a little lesser, whereas three-digit addition and subtraction, uh, are kind of below two-digit addition and subtraction. Then we have four-digit, and then we have five-digit. Yeah. Then we have single-digit three ops. Okay. So I think more and more digits that we increase, there is a significant slump or downfall in the performance, or I mean the performance does not increase that drastically, right? Because I think the examples get a little complex. So results on all 10 arithmetic tasks and few short settings for models of different sizes. There is a significant jump from the second largest model. This is also a very good observation. This was the second largest, or the current state of the previous state of the art, when this model was relatively new. You can see the jump, right? Look at the jump. I mean, here we are merely doing 55%, and here we are close to peaking at 100%, right? So the GPT-3 13 billion parameter model to the GPT-3 175 billion parameter model, with the latter being able to reliably accurate two-digit arithmetic, usually accurate three-digit arithmetic, and correct answers. Uh, you know, so yeah, I mean, what we can observe here is the model size is definitely adding a lot of value in the performance, right? And as we increase the digits, it gets a little difficult and complex for the model also. Okay. Now I think we've covered most of the graphs, and most of the graphs are around new different benchmarks and different plots, and all of them are trying to prove certain things. Now let's see what is it that we should take away from this particular model. What are the few paradigms and few I wouldn't call them theorems, but few insights that we should take away from the paper. So the first insight that is worth noting is, the law of logarithmic compute returns, which states nothing but it's simply as you increase the compute size, your cross entropy loss decreases, right? So we are simply trying to say that it is a very predictable relationship between compute and loss, right? So we call it the power law relationship with compute. So the relationship is inversely proportional. So if we keep on increasing and feeding more and more hardware and more compute, we can uh, decrease the loss and increase the performance. So we are also kind of saying that intelligence is treated as a commodity that can be purchased with sufficient hardware investment, right? So which makes a lot of sense, or at least which made a lot of sense when we had no new innovation in architecture. We knew that scaling the same architecture will get us a lot of non-linear results. Though scaling is not producing linear results, scaling is going to produce non-linear results, right? So the second insight that is worth noting is around few shot learning. So one of the most nuanced findings is that while all models benefit from more examples in the context, the slope of improvement is much steeper for larger models, right? So as I said, it's like a double engine enhancement. First engine that is enhancing your performance is your scale, which is the number of parameters. The second engine that is enhancing and magnifying your performance on top of scale is the few shot strategy, right? So few shot strategy obviously superior, but few shot strategy, when topped with the larger model, you will see a lot steep performance result, or a steep decline in the cross entropy log loss. So yeah, a larger model is not just more knowledgeable, it is a more plastic learner. Yeah, I think this is also a very very important point. I mean, this is a very important point that it's worth noting, and that also I think we will maybe note it here, which is that now we can see that these models are not only predicting the next token, right? They have the ability to predict the next token, obviously. They are not some static simulators of knowledge. Static simulators of knowledge means that they have learned the whole language modeling of the internet, of the whole world, and now they are just going to simulate what's there, right? They also have some ability to learn while you prompt them, while you inference from them, right? And uh, we will talk about that paradigm here, which basically says that obviously we the, I mean, obviously there is some correlation with the model space perplexity and its performance, but what happens is that the linguistic modeling is a broader task that it is able to do. To predict the next word of a physics textbook, the model must effectively learn physics. To predict the next word of a translation, the model must understand the mapping between languages. So what it's trying to say is that these are not simple your typical GPT-2 based next token predictor. They are also good universal approximators, and they kind of have some sort of intelligence. And in the forward pass, they also have the ability to produce a latent representation, that is not the parameter based representation, but the latent representation that can help them do the task better with only a few examples, right? So this is a very very important idea. I mean, it also kind of states that, or kinds of tries to prove that if you can predict the text well, then only you can do reasoning well. So it was a little controversial at that particular time, when they tried to emphasize a lot on reasoning. Obviously it was not able to do reasoning, but the idea was that uh, the if the objective is just next token prediction, uh, then the model obviously is good. But if the objective is to have certain variety of tasks like reasoning, like better translation, like better Q&A, like better logical tasks, then also the model is ever behaving very nicely, and the larger parameters have tighter correlation with all of these tasks, right? So I mean, this is also an important idea. I mean, they tried to prove that this is like a world model when they said that it understands the physics book and it understands the laws of physics. So understanding physics only from reading the book is very different from observing the objects in the real world and making sense of gravity and making sense of thermodynamics and liquids. So that is a lot different. So this claim was, I mean, claiming that this is a reasoning model, this is a world model, this understands how the world works, was a little overstretched, right? But yeah, this was definitely true that predicting the next word was a good idea to predict the reasoning task, or to demonstrate that you understand a few things. Okay. So I mean, they were trying to prove that language modeling itself is world modeling, but which is not 100% true. Okay. Now I think that there's one more thing that is worth noting here, which is data contamination and the overlap law. So what we are trying to say here is that we are not simply just memorizing, right? So GPT-3 was criticized that it is memorizing the internet, and it is only memorizing the internet. But the researchers kind of, proved that that they had overlap of the training data and the test data. So that's why you might think that we are simply trying to memorize, but the overlap was only a few. I mean, of a very few data set. And if you gave it a totally different data, if you remove all the contaminated examples, so data contamination is that part. If you remove all the contaminated examples, the performance of the model only dropped by 1 or 2%, right? So they found that while some contamination existed, there were some memorization and some overlap of training and testing data. But even if we removed that, the clean performance was typically within 1 to 2% of the contaminated performance, right? So this led to the empirical law that for models of sufficient scale, generalization is robust enough that small amount of data leakage do not fundamentally invalidate the intelligence claims. So what we're trying to say here is that if your model is of this particular scale, GPT-3 175 billion parameter model was the biggest model at that time. So these models tend to produce a generalized linguistic understanding of the world, and it is very robust and very anti-fragile. Even if you remove a few portions of the data that you think might be contaminated or memorized or learnt uh, or hard coded, uh, the performance merely decreases. All right. So this allowed the later research teams to proceed with training on massive internet scale data, even when perfect isolation of test was impossible. Right. So I think, yeah, these four things are worth understanding and worth noting from this particular paper, and all the plots that we saw kind of proved all of these four hypotheses. Yeah. So I think I'll see you in the next paper, and thanks for tuning in. I hope you learned something new and the idea of in context learning. Thank you.